Hello, so we're going to talk a bit about series and parallel circuits. Okay, so a series circuit is one that goes in a continuous loop the whole way around. So in series, some of our total resistance will be equal to the sum of the resistance of each component. So if the resistance of this bulb here is 3 ohms and this resistor is 3 ohms, then the total resistance is going to be 3 plus 3, which is 6 ohms. Throughout a series circuit, the current remains constant. And the reason that this is if you think about current as a collection of electrons, a moving charge, if we think about our negative drift and things like that there, then the current, the same amount of electrons are going to go through each component of the circuit. I'm going to go the whole way around the circuit. So the current in a series circuit is constant, okay? And that's important to remember. The voltage, on the other hand, the potential difference is going to vary. So as V is equal to IR and resistance of different components can vary, whereas I is remaining constant, the current remaining constant, then as resistance varies, then the voltage will vary. So what I want you to do is have a look at these two components, and they're both resistance 3 ohms, and figure out if you connected a voltmeter in series, or in parallel, across the components, what would be the potential difference that would be read. So first of all, the thing you need to look at is the total supplied voltage, which is 12 volts, and the total resistance, which is given by this equation. Okay, so the total voltage is going to be equal to 12 volts, and that's going to be the voltage of this one plus the voltage of this one. The total current is given by the total voltage over the total resistance. And we know the total voltage. Okay, so moving on to parallel. In a parallel diagram, so we've got one here, we've got our supply cell here, and we've attached a voltmeter in parallel across the supply, and we find that that is equal to 12 volts. So in parallel, voltage or potential difference remains constant, whereas the current doesn't. So again, if we think about a current as a moving charge or a moving collection of electrons, if we have our packet of electrons here, it'll move and go through this ammeter, and that'll read the total current, and then it will split through these junctions, and the way it splits will be dependent on the resistance of each junction. So here we've got 3 bulbs. The ammeters coming up here, they all have negative or negligible resistance, not negative, negligible. These bulbs all have a resistance equal to 3 ohms, and their resistance, as we've seen before, the resistance of a parallel circuit is 1 over Rp is equal to 1 over the resistance of one component plus the resistance of the other component on each branch, okay? Voltage, or the potential difference, will remain the same the whole way through, but the current will not. So the current splits, as we said about the charges, will split through these here according to our Ohm's law. The voltage remains the same, so this here, V, is constant. So as R varies, the current will vary. It is going to be inversely proportional to the resistance. So have a look at these two diagrams, and I want you to tell me what would be the current going through the first ammeter, and what would be the currents going through these next 3 ammeters, and they're all going to be equal. Also, just as a way extension, what would be the current going through a 5th ammeter coming through here? Okay, so if you want to pause and have a go at those 2 questions, I'm going to do them here, and hopefully I get them right first go. So the resistance of the series circuit is going to be equal to one component, which is the resistor, which is 3 ohms, plus another component, which is going to give us 6 ohms as our total resistance. So our voltage is equal to 12 volts, and that's going to be divided by 6 volts to give our current, which is constant, through the series circuit of 2 amps. So if you have going through this resistor, we've got R equal to 3, and we've still got a current of 2 amps. So the voltage going through that resistor is going to be V equals IR, which is going to be equal to 2 times 3, which is 6 volts. So as they're both 3 ohms, it's going to be the same. So we've got our 12 voltage potential difference coming through here. We're going to have 6 volts coming through this component and another 6 going through that component. Okay, so then the parallel circuit, working out the currents first of all. So these, as I said before, are all 3 ohms. So our parallel circuit is going to be 1 over R parallel is equal to 1 over 3 plus 1 over 3 plus 1 over 3. So that's going to be equal to 1. So 1 over R parallel is equal to 1 over 1. So the total resistance is going to be 1 ohm. We know that the supply voltage is going to be 12 volts. So if we have V equals IR, and we're looking to find out what the current going through the first ammeter here is, and the total resistance of these branches is going to be given by 1 ohm, or RP equation there, then we'll be able to say that 12 is equal to I times 1. So we're going to have 12 amps going through the circuit here. So A1 is equal to 12 amps. So looking at this diagram, we're going to be able to say that the current of going through A2 is going to be equal to A3 equal to A4, and that's just because all of these branches are completely identical. The voltage going through each of these voltmeters is constant, so that's always going to be 12 volts. So using our V equals IR again, if we say that for a 3 ohm bulb, we've got voltage is equal to 12 volts, and that's equal to our current times 3, our current is going to be equal to 4 amps. So you can see here, if we've got 4 amps coming through here, here, and here, then our total is going to be equal to 12 amps, which is what we had going through our initial ammeter. Coming out the other end, if we had another ammeter here, we would also have 12 amps as well. Okay, so I hope that clears up parallel and series circuit currents and voltages, and potential differences in resistances. All right, thank you.